Hello students of science. In this video we're going to talk about phase diagrams, cooling curves, and how it relate to water. Here on the left we have a liquid cyclohexane actually going through its triple point where solid, liquid, and gas all exist in equilibrium. And over here we have a beautiful water bubble freezing. A phase diagram talks about a couple different things about each compound. First thing we need to understand is the triple point. The triple point of a substance is the temperature and pressure, it's not one or the other, it's both, where solid, liquid, and gas phases can all exist in equilibrium at the same time. So here is my triple point. I have pressure on the y-axis and temperature on the x. Here we have solid, liquid, and vapor, or that's British for gas, I guess. And then we have right here is the triple point. That is the temperature and pressure for this particular substance where it's going to be existing as a solid, a liquid, and a gas at the exact same time. Another thing right here, we got the critical point. Critical point indicates the critical temperature and critical pressure. So this right here, this vertical line, that is the critical temperature. This is the critical pressure. If you are above this pressure right here, something is no longer a liquid. You cannot have anything that is, well, as we would call it, a normal liquid. Above this temperature here, you also cannot have a liquid. You're instead going to only have vapor, or you're going to have some other things going on. But the critical point tells you that is the critical pressure and the critical temperature. Anything above that, this way or that way, to the right or above, it is not going to be a liquid. Liquids can only exist below those. Here is a phase diagram that I want you guys to fill out. You should find it on the page opposite of your notes. Take a second, flip over there, and fill this in. So temperature is going to go on the x-axis, starting at low temperature here, absolute zero, all the way going up to high temperatures. Pressure is going to go on the y-axis, starting at low pressure there, pretty much full vacuum, going up to insanely high pressures up there. Solids occupy this upper left space there, then we have liquids, and then we have gases right there. The triple point, as I mentioned, is represented right here. It's the part where solid, liquid, and gas all exist in equilibrium at the exact same time. Critical point is represented right here, which means that this is the critical pressure over here. Everything above that cannot have a liquid. And the critical temperature is this line right down here. Everything to the right of that cannot be a liquid either. Melting is going to be represented as solid going to liquid. And if you have the chance, I would recommend that you use red for endothermic reactions and blue for my exothermic reactions. So solid to liquid, of course, is an endothermic reaction. You have to apply heat to make a solid melt. And if you go in the opposite direction where you are pulling temperature away, that of course is going to be freezing. That's our exothermic reaction. Liquid to gas, that's going to be evaporation, another endothermic reaction. And gas back to liquid is condensation. Solid to gas, again, those are my slightly unique ones here, but going straight from solid to gas, which you can only do at this line right here. So only at certain temperatures and pressures. Solid to gas sublimates, and gas back to solid is deposition. What you will notice right here is all of the endothermic reactions that absorb heat is what happens when you're going to the right. All of these are actually pointing to the right if you are looking for those. My exothermic reactions are all going to be pointing to the left. So this is how you fill in the phase diagram with the different parts of it. Another thing we need to talk about is a cooling curve. A cooling curve is a line graph that shows the changes in state of a substance as it cools or it heats. Here's a rough schematic of one. We'll fill out one in just a moment. States of matter are always going to be at an angle. So here are my three ones that are going to be at angles. This one, of course, is going to be gas. So I start off at the highest temperature and I go to the right over time and I let it cool. So after enough time, gas will cool down and we're going to get, of course, liquid, cool that down some more, and eventually we get solid. We're going to skip sublimation and deposition on here because we're going to be doing this at pressures where that doesn't happen. So just my traditional gas, liquid, and solid. Horizontal stretches are going to demonstrate a change in state. So here I had gas, liquid, solid, but these horizontal stretches right here and here are going to represent a change in state. So if this was a gas and this was a liquid, this right here represents condensing. As I go to the right, that temperature is actually not going to change. This is very counterintuitive. You leave something sit out, you just expect it to just continuously go down in a straight line, but it's not. It's going to plateau off while it changes in state. So during the act of going from gas to liquid, that cooling curve is actually going to have a horizontal flat stretch, which of course means that going from a liquid to a solid, that's going to be another change in state that's going to be freezing. Once again, that one is going to be horizontal. So my horizontal stretches are going to be state changes. The angle ones are going to be states of matter: gas, liquid, and solid. The weird counterintuitive part here is even when you are adding heat or removing heat during a state change, the temperature does not change. If you are boiling water and it is at this state change here, imagine we're going to the left, it doesn't matter if you turn the heat up higher. That water will not increase in temperature because it's absorbing all that heat and using that to go into the gaseous state. There cannot be a change in temperature while it's doing a state change. That's where all of that energy is either coming or going from. More on that later. Here we have a cooling curve of naphthalene, C10H8, also known as the stuff that you put in mothballs. Here it is going from liquid to solid. So its freezing or melting point, remember those are essentially the same thing, it's just what direction you're going, is 80.26 degrees. On my y-axis here, you'll see 80 degrees right around where this thing starts to level off and get flat. So remember, that's a liquid right there. States of matter are at angles and changes in state are at horizontal. So this is a liquid, which means that this horizontal plateau right here, even though the whole thing is cooling off, the temperature is not changing. That's because right here, it's freezing. During this freezing process, there is no change in temperature, even as the whole thing is quote unquote cooling off. That's because it's changing from a liquid into a solid. During this process, the temperature will not change while it changes state. On the opposite page of your notes, you have another diagram. This is a cooling curve. I want you guys to fill this in with me. So remember, change in state is horizontal. State of matter is an angle. That's worth writing down in there. So here's going to be my gas. As I cool down more, I'm going to reach my next angle. That, of course, is going to be liquid. And then I'm going to reach my final angle. That is going to be solid. Those are my three states of matter: gas, liquid, and solid. Of course, my changes in state are going to be my horizontal. And as I cool off, gas to liquid is going to be condensation. Remember, that's going to be an exothermic reaction. Heat is actually being given off. It's going away. Liquid to solid, of course, is going to be freezing. So these are horizontal, change in state. Let's say I was to go the opposite direction and almost heat it up. You could call this a heating curve, solid to liquid to gas. Well, solid to liquid, of course, is going to be melting. And liquid to gas, of course, is going to be evaporation. So my horizontal stretches, change in state. Angles are going to be my different states of matter. Finally, we got to talk about water and how it relates to all this. Water is a polar molecule which forms OH hydrogen bonds between molecules. So here's my H2O right here, and I'm going to have a hydrogen bond between this slightly negative oxygen and this slightly positive hydrogen right there. So these are intermolecular bonds. The H bonding holds those molecules tightly together, meaning that it takes more energy to change state. That's why water is so difficult to go from the liquid into the gas state there. These strong hydrogen bonds and how each water molecule is going to be bonded to 4 others means it takes a lot of energy to change state. If you did not have hydrogen bonds, water would actually be a gas at room temperature. That would make drinking things very difficult. Swimming would basically suck. Here we compare water to another molecule that's very similar to it. Here's water, H2O, and here's methane, CH4. Very similar molecular masses, wildly different properties. Water is a polar molecule. It is slightly positive on the hydrogen side, slightly negative on the oxygen side. Methane, however, is a nonpolar molecule. This one will not form hydrogen bonds. This makes water have vastly different properties. Water's boiling point is 100 degrees Celsius. Methane is negative 162. At room temperature and pretty much freezing temperatures, it's still a gas. Water's melting point is 0. Methane's melting point is negative 183 degrees Celsius. You have to take out a lot of energy from these things for them to start bonding with each other. Water doesn't have that issue because of those very, very strong hydrogen bonds. As a result of this, hydrogen bonds push your cooling curve up significantly. The cooling curve for methane would be very difficult to do because you'd have to get it down below a negative 183 degrees Celsius. As a result of these hydrogen bonds, the cooling curve is way higher on water, and this is very important for life as we know it.